Okay, well, to work with here in section 5.6, all we're going to do is pick up right exactly where we left off with section 5.5. 5.5 we were learning how to integrate using substitutions. Well, this is the exact same thing we're going to do here. We're just going to do another method of substitution. When you look here at Theorem 7, basically what we're doing here is, again, we're going to be locating, when we're asked to take an integral of a function, we're going to want to focus on finding a brand new function in there, finding its derivative. But this time what we're going to do is also change up the terms of integration, of where we're starting and when we're finishing. And what this does is, you know how in the last problems we always found u and du, we went in there and did the integral, and then we did plus c. Well, this is kind of a more way to do it with a definite way of going from, like, let's say 1 to 5 or -1 to 3. Okay, and what we were going to do is have to change our bounds of integration, as well as not only finding out what u and du are, we're also going to change our bounds, because u and du are in terms of u, but when we're given these original functions, everything's in terms of x. We're going to have to change everything around in order to do that. So looking at these steps right here, they're very important. We're going to want to identify both a function and its derivative, and then we want to replace, obviously, the gx with u and the g prime of x with du. And then the next part is we're going to want to change the bounds according to what we say u is equal to. And then we integrate. Okay. Theorem 8 is just all about ways of when you're asked to find the areas under a curve. If things are symmetric, then you can definitely use some shortcuts if you have to. Obviously, whether you go from negative a to a or you just go from 0 to a and double it up, it's the exact same thing. So yes, if you assume that, it looks like you can actually assume correctly. And the same thing if you have an odd function. Then since you have an area below the curve, which tends to be negative, and an area above a curve, which tends to be positive, what this is saying is they do cancel each other out, and you get an overall area of just 0. Okay, and then with this next point is really what I want to take the time to really iterate, is every time we've been doing so far, we've been finding the integral or the area under a curve. It's always been with respect to the curve and the x-axis. Well, what this example is showing you is, what do you do when you have two curves and not necessarily the x-axis, okay? Then all you do, and this is the key, is you take the upper curve, subtract the lower curve, and you just integrate it like that. So you can almost consider the area to be the integral from a to b of f of x dx. So just do that like we normally how to do, and then just subtract off the area from a to b of g of x dx. And it's just like that, okay? All right, so it looks like if your notes are anything like mine, it accidentally starts, you're like, oh wait, that's example 2. What happened to example 1? Just go down to the next page, and then we're going to come back to that one, okay? So starting here in example 1, we want to practice evaluating the following. The integral from 0 to pi, so now we have a definite integral of 3 cosine squared sine x. And with this one, we just kind of want to go about the integration process. We want to identify a u, and we want to identify a du. Okay, well, if I go to the one that has the power as being u, we're going to say, let's let u be cosine of x, and then du is going to be negative sine x dx. Okay, going to our function, it looks like I have, obviously, u, because it's going to be u squared, and there's my sine x dx. The only thing I have different is I've got this 3 up front, and I really needed 1. I need a minus sign, and I needed 3 to go away. Okay? So if I put, in order to get this to work out nice and pretty so I can see my u and my du just fine, I need a negative 1/3 in here, so that way this 3 will go away. And let's try this out, just like this. Okay, so what I added inside the function, or what I multiplied to the inside the function, was this. I'm going to have to do the reciprocal of it out front, so that way I don't change everything too much. So that'd be a negative 3, and just double check. Negative 3 times a negative 1/3 would be a 1, and I get my original function back. Okay, so now we can write it as negative 3 times the integral from 0 to pi. This all goes away, the 1/3 and the 3. So that's just kind of going to check. And what I have is then a negative sine x dx, where there's my du. So I have my u squared and my du. Okay, so now Normally we would start right there and we would do our integration process and have a plus c. This is where the new thing is going to come in, is what do we do with these bounds? Because these bounds right now, since they're the original bounds, they're in terms of x, and we need to change them in terms of u. And so right here are the exact steps on how you're going to do it. Okay, so this is what I would write out. Right now we know that, gosh, that was horrible. That should have been a W, y'all. That was funny. Okay. We know that when x is equal to pi, we want to change it around. Well, then u is going to be cosine times pi, okay? Or u is equal to cosine times pi is -1. When x is equal to 0, then u is cosine of 0, just plugging into what our u equals, and so then u is equal to 1. So this is saying the exact same thing as -3. Instead of 0 to pi, I'm going to go 1 to -1 of u squared du. Okay, and then just to finish this out, let's go ahead and then do our integral. Take the integration, so it's -3 would be 1/3 u cubed evaluated from 1 to -1. Or basically I have -u cubed 1 -1. Now remember, it's always the upper bound, so -1 cubed minus the lower bound, 1 cubed. So together we're going to get a final answer that looks like 2. And that right there is how we do the other method of substitution. So really it's all the same thing. All you have to do is just change your bounds, and that way you don't have to go back in and plug in what cosine was. It's like right here, after we would take the integration, we would say u was cosine x, and then go from there, so we don't have to do that anymore. All right, let's go on to example B. Again, we want to start out by identifying like a u and then our du. So I usually go to the part that has a exponent to it, and I say, let's let that be u. So let's say u is t squared plus 1. Then du is going to be 2t dt. Okay, so right away I know I'm going to have to put a 2 right inside of here. So that way everything's present for my du part. And then since I put a 2 in, I'm going to counterbalance it with a 1/2 out front. All right, and other than that, let's change our integration. So if x is equal to the negative square root of 7, then u is going to be the negative square root of 7 squared plus 1, or u is going to be, the negative square root of 7 squared plus 1, so it's going to be 7 plus 1, which is 8. And if x is going to equal 0, that's saying then u needs to be 0 squared plus 1, or u is equal to 1. Okay, so let's take all this information together and get ourselves a brand new integral. So it's going to be 1/2 times the integral, instead of -7 square root of 7 to 0, it's going to be the integral of 8 to 1 of u to the 1/3 du. Let's double check. The 2t and the dt is my du. That part is u to the 1/3. Got the 1/2 out front. This negative square root of 7 switched over to a 8. And the upper bound of 0 switched over to 1. All right, so now we can go back to taking the integration. So 1/2, we add 1 to that, so 4/3. Divide by that new exponent. And we're going to be evaluating that from 8 to 1. So kind of cleaning this up a little bit. Let's see. 1/2 times 3/4 u to the 4/3 from 8 to 1. It looks like there's not really much we can do with that. So 3/8 u to the 4/3 from 8 to 1. Okay, so we have 3/8, and it's going to be the upper bound. So not u, but I'm going to plug that in this time. So 1 to the 4/3 minus 8 to the 4/3. Okay, so 3/8, 1 to any power is 1, and this is saying the cube root of 8, which is 2, and 2 to the 4th is 16. So we'll get a final answer of -15 times 3, so -45 over 8. Okay, well let's go on to our next example, part C. Okay, so here with C, again, we just want to identify a u and a du, and so you have choices here. We've got tangent and we have secant squared. One needs to be the function, u, and the other one needs to be du. Well, I know, or hopefully y'all remember, that the derivative of tangent is secant squared, so obviously that's a great pairing to go with. So let's let u equal 2 plus tangent of t over 2. And then in that case, du is going to be 0 plus tangent, the derivative of tangent, which is secant squared, t over 2, times the derivative of that angle, which would be 1/2 dt. Okay, so kind of going back to our main function just for 1 second real quick. We have the u part, so all of this right here is going to be my u. I've got the secant squared t over 2 dt. All I have extra is this 1/2. So I'm going to put a 1/2 in there and counterbalance it with a 2 out front. So right now we're looking at the integral. 2 times the integral, we're going to get our new bounds here in just a second, but of basically u and du. Okay, so that looks nice and pretty. Let's get those new upper and lower bounds for us. Okay, so if t is equal to 0, what that means then is u has got to be 2 plus tangent of 0 over 2, which is 0. Okay, and u is equal to, well, it's 2, and then tangent of 0, well, the y value at 0 is 0, the x value is 1, so 0 over 1 is 0, so just u equals 2. And we're done with that one. So it looks like the upper bound, so when t equals 0, then u is going to be 2. That's our upper bound. Again, when t is negative pi over 2, let's go with that. So u is going to be 2 plus the tangent of negative, so pi over 2 would be pi over 4. So in that case, u is going to be 2 plus tangent of pi over 4. Well, if it was positive pi over 4, it would be 1. Since it's negative pi over 4, we're down in quadrant 4, and that would be at negative 1. So 2 plus negative 1 gives us an overall u value of 1. So we're going to integrate from 1 to 2 of u du. Okay, so 2 times 1/2 u squared, evaluated from 1 to 2. Okay, if we want to go ahead and just clean that up, then it's just u squared, evaluated from 1 to 2. So it's 2 squared minus 1 squared, which is 3. Well, that came together nice and pretty for us, didn't that? Let's go to the next one.